Hello everyone, and welcome to today's video where we will go through some of the most recent questions from the topic of Principles of Flight, and today we'll go through mixed topics, so nothing specific. However, all the questions I've selected for today are a little bit tricky and not so obvious, so I hope you will enjoy the video. So going into question number 1, how does an increase in weight affect critical alpha? Of course, first things first, I just want to remind you to remember that the critical alpha or the critical angle of attack is the last angle of attack at which your wing will produce lift. So this is a common misconception. Alpha crit is when the aircraft is not yet stalled. It is just before stalling. However, remember that aircraft weight will significantly change our stall speeds. However, remember that the critical alpha or the stalling angle of attack will be mainly based on the aerodynamics of the wing and the design of the wing. So if you are heavier, you need to produce bigger lift for the same in order to keep flying straight and level. So you will naturally fly with a higher angle of attack when compared to a lighter aircraft. This is why your aircraft will stall sooner and have worse stalling characteristics. This, however, does not mean that the stalling angle of attack will change, because as I just said, this will be based mainly on the design of the wing. So in this case, remember that the weight will not have any effect on the critical alpha, however, it will definitely have an effect on your stalling speeds. For question number 2, during a training flight, accelerated stalls are voluntarily carried out using excessive stick inputs to pull up during stall recovery. The airspeed is kept below 90 knots throughout these maneuvers. The next exercise is a demonstration of entry and recovery from a spiral dive. As the spiral dive develops, the speed is allowed to build up towards 130 knots, given the following airplane limitations, which is the correct statement. So this is a very practical question, and you'll see the effect of these things and these exercises in real life once you start your flying phases of the training. However, the EASA here wants you to spot something very, very critical and important, which is the maneuvering speed, or the VA. So what the VA is the VA is a speed which guarantees that the aircraft will stall before it goes into an overload situation, meaning where the loads on your aircraft are bigger than the maximum structural loads allowed. So the VA makes sure that if you're flying below that speed, you will basically not overstress the airframe because the aircraft stalls before that happens. If you're flying at the speeds greater than VA, you will actually stall later than that happens, meaning there is no aerodynamic safety margin built into aircraft above these speeds. And this is very important. This is why we should never do any excessive or full control deflections above the maneuvering speed, or the VA. Of course, here the other speeds, VS, which is our stall speed in a clean configuration, VNO, which will be our normal operating airspeed. This is the green arc on the speedometer or the airspeed indicator, and the VNE never exceed. So anything after the VNE will be our red arc. This is the speed above which the aerodynamic loads on our aircraft are bigger than the aircraft is certified for. So in this case, if we're flying above the maneuvering speed, we should never apply full or abrupt inputs into control surfaces, because we can exceed the loads. And below that speed, if we do so, we will first stall before exceeding those loads. So this is something to remember. This is a very practical question and very often asked by examiners during CPL exams and flight instructors. So going back to the possible answers, if too much elevator is used, the recovery from spiral dive, the airplane may stall and enter a spin. So no, because of course the airplane, here the threat will be exceeding the loads. Careful application of the elevator must be used to recover from the spiral dive to avoid excessive load factor. This will be correct. So again, above VA, never use full deflections of the surfaces and use them carefully. For question number 3 now. The difference between our indicated airspeed and true airspeed will. So now this is a classic question which we can very simply answer using the chicken tikka masala mnemonic, or eat chicken tikka masala mnemonic, meaning what happens with different airspeeds as we climb or descend. So if you are climbing with constant indicated airspeed, then of course your true airspeed will continue to increase. So the difference between the two increases with altitude. However, it will also conversely decrease with altitude. So there it is, the answer very quickly for that question. The same relationship will be between IS and Mach, or between TAS and Mach number. And you can answer this very, very easily. Remember the eat chicken tikka masala mnemonic, essentially, which will be our calibrated and true air Mach number. So if you are climbing with one of each constant, the others will rise. And if you're descending, of course, the same will be true. However, in the opposite sense. And now for question number 4. An aircraft in straight and level flight at high altitude and at high Mach number encounters turbulence. During an updraft, the angle of attack increases, and if airspeed remains constant, what happens to the margin? So this is a little bit tricky because remember that the margins, if we are climbing, for example, our margins will start to decrease. And this is something that is very well shown with the coffin corner, which of course, as we are climbing higher, our margin between the low speed buffet or the stall speed and our high speed buffet, the margins keep decreasing, and ultimately we come to our aerodynamic ceiling, which is a place at which we are essentially both in the high speed buffet and with when we are flying almost at our stall speed. So of course there is a margin at which aircraft fly, meaning there is sufficient distance between the high speed buffet and the low speed buffet. However, if our angle of attack increases at high altitudes, this margin will decrease. So the high speed buffet margin will decrease, and also our low speed margin buffet or the low speed stall margin will also decrease, meaning this will be slightly dangerous. The same will be true if our load increases, so during a turn, and if our weight increases, which is not that possible during a flight. However, for the exams, I've seen questions asking about exactly that. And now for question number 5. The use of ailerons induces adverse aileron yaw, and this occurs as a result of that. So the adverse aileron yaw is something that a lot of examiners like to ask in real practical exams, as well as the flight instructors. This is a very, very beloved question. I've seen both on my example and from my colleagues that this question has been asked so many times. So it's great to know how the adverse aileron yaw works and drill this into your mind. It's a very simple principle. Of course, when you are turning, you are deflecting ailerons in your aircraft. So what the deflected aileron does, it essentially changes the camber of the wing. And the changed camber, so the changed positive camber, all it does, it increases the lift on that side. So remember that if you are deflecting the aileron, you'll increase the positive camber on one wing and the negative camber on the other, meaning you change how the lift production of that wing works. Of course, now, when we have more wing, the upper wing that is going up during a roll, of course, produces more lift. And more lift also means more induced drag. And this increase in induced drag, what it does, it creates this very tiny, however pronounced, especially in small aircraft, yawing motion towards the upper wing. So what you need to do, you need to always put some rudder towards the side you're turning in order to keep a balanced flight. And you'll see that this is very easily demonstrated once you fly in the air, because if you do not input the rudder towards the turn, you'll see that the bow or your balance indicator will go very much offside. So remember that the upgoing wing is producing more drag than the downgoing wing because it produces more lift, so it produces more induced drag. So this is a very simple, however, a very good thing to remember and memorize, because the principles will apply for many other things in aviation and when it comes to the drag theory. And I'll just add on top of this that there are also some means of reducing the adverse aileron yaw. For example, phrase ailerons, meaning one aileron goes more down than the other goes up, and vice versa, as well as we have some ailerons that are protruding into the airflow from the other side, changing the drag on the other wing. So phrase ailerons, for example, will be a great example of something that is also asked during the exams that can help us overcome the adverse aileron yaw. And now for the last question of the day. So an aircraft departs with maximum takeoff weight and with the CG on the aft limit. On the return flight, due to no payload being carried, the CG shifts from the forward to the forward limit. How will the static stability have changed on the second leg? So when the CG moves more forward than it was before, we will have increased stability, but decreased maneuverability. So the static stability, of course, will be increased. So this is a principle that is also very important to remember for both principles of flights, performance, flight planning, and mass and balance. And I believe some questions from GNAF as well can ask this particular question. So for the CG positions and how they affect your flight, it is very good to remember that with increased stability, we have decreased maneuverability, and that is true for the forward center of gravity. When the center of gravity is aft, as for example in fighter jets, we have increased maneuverability, but decreased stability. And of course, there are some other implications when it comes to the CG position. So of course, if the CG is more forward, we have greater stability. However, we will burn a little bit more fuel and we will have decreased stalling margins and the decreased range. And that is because we now need to produce more lift in order to fly straight and level. And this is because the forward CG will need to be overcome by a greater force, downforce on our tailplane that will position our aircraft back into level flight. If the CG is more aft, then less downforce is needed to overcome this moment, and meaning this downforce, of course, is positioned down, so it increases the weight component that needs to be overcome by the lift component going up. And so this will be it. It's good to remember more stability, less maneuverability when CG is forward, and then more maneuverability, but less stability when the CG is aft. And this will be everything for today. So thank you so much for tuning in. I hope this will helpful. I wish you all the best with your upcoming exams. If you have any questions, as always, feel free to ask. And I hope to see you in the next video. Bye-bye.